Hey, this is a follow-up video to the previous one, topic 2.9. And in this video, we're going to look at how a transformed data set could be used to help us predict a response. All right, so as an example, we have a scatter plot showing the relationship between the number of police officers, and those numbers are measured in thousands. So it goes, 10,000 up to 90,000 on, that's a scale. And the response variable is the violent crime rate, okay? And this is measured in crimes per 100,000 people, I believe. Okay. And so this is the raw data, right? And what you'll notice is that a linear model could work here, but there's a distinct curve in the relationship. Right, if we look at the points, right, they tend to follow a curve more than they do a line, okay? And so we might not want to fit a linear model to this data, okay? Here is a residual plot, which again, you can kind of see the curve nature here, right? The residuals kind of curve up and then curve back down, right? There's one point here that seems to be having high leverage, right? Has an extreme X value. Here's the equation of the line, okay, not of a curve, but if we fit a line, this would be the equation, okay? And the R-squared value is only around 0.51, right? So only about 51% of the variation in crime rate is being explained by the number of police officers. Okay. All right, so what do we do if our scatter plot exhibits a curve pattern, right? We can't like change the numbers in the data. Well, in a way, we kind of can, right? We can perform a transformation, a function to the data. Okay, so here, model 2, we're looking at still the number of police officers measured in thousands, but we're looking at the natural log of the crime rate. Okay, so we've performed an operation, a function, to one of the variables. Okay, now does this make the data any more linear? Maybe, but I mean, I'm still noticing, right, a curve pattern, okay? So this particular transformation doesn't really help achieve linearity, okay? You can see the residual plot also still has a curved nature to it. And look, the R-squared actually went down, right? So now it's 0.39, whereas previously it was 0.51, okay? So yeah, taking a logarithm of the response variable crime made the relationship less linear. Here's one more model. Okay, and what this model does is it transforms both variables, right? It transforms the explanatory variable, so now we're not looking at the number of police officers, but the natural log of the number of police officers. And it also uses that same function on the response variable, so the natural log of the crime rate. Okay, and now we can see a much more linear pattern. Okay. And then that is evidenced by the residual plot, right? It looks a lot more random, and the R-squared value is a bit higher than the first two models. Right now it's at 0.67. Okay, so here, 67% of the variation in the natural log of crime rates is being explained by the model with natural log of police officers. Okay, all right. So here I forgot to mention that, so here's the equation of, the linear model, okay? So it's not just y hat, it's the natural log of y hat. And we have an intercept, and then we have a slope. And then instead of just x being the explanatory variable, it's the natural log of x. Okay? And remember, that's the reason why those natural logs are in our equation is because those were the transformations we applied to both the x and the y variable. Okay. All right. So what I'd like to do then is I'd like to take this equation from model 3, right, and use it to make a prediction, right? I'd want to use this model because it is the best of the 3 models, right? It's the most linear of the 3. It has the highest R-squared, right? So this should be the model that we use to make predictions. All right, So here's a prompt at the bottom, okay? Use your model, which is gonna be model 3, to predict the violent crime rate for a state with 25,400 police officers. Okay. Now, the original values were measured in thousands, so this would be 25.4. Okay. All right. So let's go ahead and do that. Okay. I think I'll try to do it right here. Okay. So we can write the natural log of y hat equals 4.886 plus 0.5365 times the natural log of 25.4. Okay, so all I've done so far is I've taken the x value, which again has to be measured in thousands, and I've substituted it for the x variable in our linear model. Okay, now I'm going to use the calculator here to do some of the work. Okay, so 4.886. So I'm evaluating the right side of the equation, right? The expression on the right. 4.886 plus 0.5365 times the natural log of 25.4. Okay, and so the expression on the right side of our equation simplifies to 6.62. Okay, so now I have the natural log of y hat equals 6.62. Okay. Well, that is not the predicted violent crime rate. It's the predicted natural log of the violent crime rate. Okay. So what we have to do now is we have to use an inverse operation to get rid of the natural logarithm. Okay. And so I'm going to use a base of e. So I'm going to use ln y hat as the exponent of base e, and I'm going to use 6.62 as the exponent of base e, right? Since these expressions are equal, right, placing a base e below them will still make, they're still equal to each other. Okay, all right. So e raised to a natural log, right, those are inverse operations, so they cancel each other out. So we're going to get y hat. And then on the calculator, all I need to do now is do e raised to the 6.62. Okay, and we get about 750. So approximately 750. Okay. All right, so you know, calculating a predicted response was a bit more involved here because of the fact that we had natural logarithms in our equation, and we had to use some inverse operations to remove them. Okay. But yeah, that's pretty much it. I think maybe for fun, right, why don't we, even though Model 2 was not a good model, right, why don't we just practice using Model 2 to predict as well? I think that would just be good practice. Okay. So if we take Model 2, right, and we want to use this model to predict the number of violent crimes or the violent crime rate, right? We're going to go ahead and substitute 25.4 for x in this model. Okay, let's change the color here. All right, so we're going to have the natural log of y hat equals 6.004 plus 0.0163. Okay, now it's just x, right? There's no logarithm with the x. So all I need to do is substitute 25.4. Okay. All right. So because the expression on the right is all numerical, I can evaluate that. 0.004 plus 0.0163 times 25.4. Okay, so I get 0.418. So the natural log of y hat equals 0.418. Okay, and then like what we had to do with Model 3, right, to get rid of the natural log, we're going to use an inverse operation. Okay, so I'm just going to put a base e below each expression, right? So this is my caret symbol. So what I'm trying to write is e raised to the natural log of y hat, e raised to the value 0.418. Okay, so these are inverse operations, so they cancel each other out. We get y hat, and then we'll use the calculator to do e raised to the 0.418. What happened here? Okay, got 1.51, which does not seem right. 1.51. Okay, let me, oh, I know, that was a 6. Okay, I knew that didn't look right. Okay, let me backtrack there. I apologize. Okay, so this was a 6. Okay, so we had 6.004 plus 0.0163 times 25.4. All right, so that should have been 6.418. 6.418. And then now I'll do e raised to 6.418. Okay, 612, right? That number makes a bit more sense. Yeah, let's call it 613. Okay, so that was a typo, that was a typo. Okay, so using model number 2, right, we would predict a violent crime rate of 613, and using model number 3, it gives us a different prediction. Okay, both of these models were of transformed data, right? Model 2 transformed the y values, and model 3 transformed both the x and the y values. Okay, so between these two, right, this is probably the prediction we would rely more on because it's based on a model that just has a better fit to the data. Okay, but I just wanted to demonstrate how to make predictions with these different types of transformed models.